Okay, so the reason why we are looking at Newton's laws of motion is because through Newton's second law of motion, we are able to work out something called the resultant force. And using this resultant force, from what we have, F is equals to ma, from that relationship, we can work out the acceleration. So during this lecture, you're going to see how the resultant force is worked out for two different directions, a direction which is horizontal and a direction which is vertical. We have two different cases here. We have a mass on a flat surface. So this mass has got, as you can see, this block has got a certain amount of mass. Then because of that mass, and since this block is on the surface of the earth, this particular block has got weight. Weight being the pull of the earth on this particular block. The weight of this block is being directed downwards like that, and this weight is being exerted on this flat surface here. Okay. The flat surface is not happy about this, so according to Newton's third law of motion, this flat surface exerts an equal but opposite force on the box. So at the end of the day, because the weight of the box and the reaction of the flat surface pushing against the box, these things are equal but opposite. That's why this particular box does not sink or does not lift off the horizontal surface. There is also another force, which is F, which is the force pulling the box in this particular direction here. So we expect in this case, if this force is large enough to pull this box in this particular direction, and since the box is going to move to the right, there's going to be another force, which is the friction force, which will oppose the movement of this box like that. So the friction force always opposes the movement of an object, and it is directed in an opposite direction like this. So with these forces, basically in this setup we have a number of forces, and these forces, as you can see, it looks simple. Just a minute, I'm coming back. So as I was saying, even in a simple setup like this one, where you have an object just lying on a table or lying on the floor, there are actually a number of forces which can work on that particular object depending on what you want to do. Okay, so with this number of forces, some of them acting vertically, others acting in a horizontal direction, there is need for you to work out one force. So you need to add these forces. You need to add the forces acting in the horizontal direction. You need to add the forces acting in the vertical direction, so that you can have something called a resultant force. So once you have this resultant force, will have a certain size, because force has got size. Okay, this resultant force will have a certain size. It can be positive. So if you've got a positive resultant force, that means that the acceleration resulting from that resultant force is going to be positive. So your object is going to move faster and faster. If your resultant force is zero, meaning that the resultant force does not exist, in that particular case, your object will either remain at rest or move with constant velocity. So there will be no change in the velocity of that particular object. That is if the resultant force is not there. The resultant force is equal to zero. So after you add these particular forces, the other case you can have is that your resultant force can be negative. So if the resultant force is negative, in that case, then the resulting acceleration is going to be negative. So a negative acceleration will cause the velocity of your object to reduce until it comes to a stop. So the one thing you can do with these forces acting on the object is you can use them to work out a resultant force. Once you have a resultant force using these forces, then you can use that resultant force to find the acceleration of the objects. With acceleration in the bag, then you're able to do all the normal things you expect to do. For example, you can predict the velocity of the object. You can also predict how much distance has been moved after a particular distance. Okay. And there's also this other case where you have a mass on object. So in this case, you've got an object of mass m. So this particular object, since it has got mass and is somewhere on Earth, this particular object is going to have a weight, which is what we have here, Fw, and this weight is pointing down. Then, since the object is supported by a rope, like this, which is a rope or a string or a cable, there is a tensile force which lives inside this rope, and that's what we are showing here. It is pointing up. So in this case, where you've got an object of mass m on a flat surface, and also in this other case where you have a mass being supported by a rope, we are going to work out the resultant force, and we're going to use that resultant force to see if we can obtain a value of acceleration or an expression of acceleration, and how that acceleration can be used. So we're going to start with the box on a flat surface with these forces. So the direction we're interested in is the vertical direction, which is the y direction. We are also interested in the movement of the box along the horizontal or parallel to the surface. So we start with the vertical direction. So in the vertical direction, as you can see, if your box either does one of two things, if it sits motionless on your surface or the table, or it moves on the table. In either of those cases, the height of the box doesn't change. It remains the same. So there is no change in the height of the box. Okay. So since the position of the box does not change vertically, it stays the same, there is no acceleration along the y. Okay? The box does not experience any change in its velocity in the vertical direction. It's not gaining any height, it's not losing any height. The other thing we do is, for you to work out the resultant, you need to choose direction, and those directions need to be assigned signs. So in this case, any force pointing up above the incline, we choose that to be a positive force. Any force pointing down below the incline, we choose that to be a negative force. So in this case, since the normal force, which is the reaction of the floor against the weight of the box, is pointing up, is directed up, this is chosen to be a positive force. Then the weight of the box, which acts downwards like this, we choose that to be a negative force. So along the y direction, our resultant force, we can obtain our resultant force from these two forces. So our resultant force along the y direction, the summation of Fy, the forces along the y, is going to be the normal force, which you have chosen to be positive because it's pointing above the incline. So it's going to be plus Nf plus the weight of the box, which we have chosen to be negative because it's pointing below the incline. So with this, when you carry out this addition to find what our resultant force is supposed to be, in this case, we end up with the resultant force along the y direction being equal to the normal force minus the weight of the box. With this resultant force, we can use this resultant force in Newton's second law of motion, like this. The resultant force along the y direction is equal to the mass of the box multiplied by the acceleration along the y direction. So in this case, the resultant force, we have it won't change. It's just the normal force minus the weight of the box. Then equals to, we multiply the mass of the box multiplied by the acceleration. However, as I have mentioned before, the position of the box along the y direction or in the vertical direction does not change. So it stays the same. So if the position along the y direction does not change, it means that the acceleration along the y direction is equals to 0. So in place of this summation of the forces, we actually put an expression of resultant force, which is equals to Fn minus Fw equals to the mass multiplied by the acceleration in the y direction. The acceleration in the y direction is equals to 0 meters per second. Since there is no change in position of the box along the y direction, so you put that there, we end up having the resultant force, which is Fn minus Fw equals to the mass of the box multiplied by 0 meters per second squared. So when we do this, mass multiplied by 0, this gives us a 0 this side. With that, we end up having the normal force minus the weight of the box equals to 0. And this, when you take this minus Fw, the other side, you end up having this result, which is the normal force is equals to the weight of the box. So what this tells you is that whenever you have an object of mass m lying on a flat surface, this flat surface can either be a floor or it can be a table. So whenever you have an object with mass m lying on a flat surface, this object has got a weight, and this object exerts a weight on this particular flat surface. However, the flat surface is not happy about the fact that the object is exerting a weight. So the flat surface exerts an equal but opposite force, which is the normal force. So what you learn here is that as long as there is no acceleration along the y, the reaction, which is the normal force of the surface with which the surface is going to push against the mass, is going to be equal to the weight. So your desk or your floor is going to generate a force, a reaction force, which is equal to the weight exerted on it. The force is equal but opposite. Equal in size but opposite in direction. So that's the first thing we learn here. That's what you're being shown here. That if you have a mass on a flat surface, this mass will exert a weight on the flat surface. The flat surface will not sit idle. It will push back with a force which is equal but opposite. That force is the normal force. Are we clear? On this first result we get as a result of applying Newton's second law of motion in the vertical direction. Is it clear?
Yes, sir, clear.
Okay. So that's what's happening in the vertical direction. Now we move on into what could happen in the horizontal or in the x direction. Now in the x direction, a couple of things could happen. Okay? But before we look at what could happen, let's look at the forces which are acting in the x direction. So in the x direction, when it comes to our box, there is this force F, which is trying to pull the box this particular to the right. Okay. Then as the box is as we are trying to pull the box to the right, there is another force which is called the friction force, which is trying to oppose the motion of the box. So we have got two forces here. There is a pulling force F, and there is a friction force which is attempting to oppose the motion of our box. Now, when you have something about to move on a flat surface, usually when it comes to choosing direction, I would advise that you choose the direction in which the box is moving to be the positive direction. So here you've got two directions. You've got either this side or that side. But since you're pulling the box is more likely to move to the right. So we choose this right-hand side to be the positive direction. If we choose that to be the positive direction, then the left-hand side is going to be negative. If the box was being pulled to the left, then we would choose that to be the right-hand side, then the opposite direction will be the negative. So my advice is choose the direction in which the box is moving to be positive. Okay, so when you do that, so we end up having a pulling force, which is F, to be positive, and there is this friction force which is going to oppose the movement of the box, and that's going to be a negative force. So we can work out the resultant force along the x direction based on these two forces as follows. So along the x direction, the resultant force is going to be equals to the pulling force, which is positive, plus a negative friction force. So when we add these, we end up having a resultant force Fx, which is equal to the pulling force minus the friction force. So this is the expression of resultant force along the x direction based on what you have seen. Now that we have an expression of resultant force, which is good, a good thing, we're making progress. The next thing is to consider what could happen to the box as a result of this resultant force. So the box, the first thing, the simplest thing which could happen really is that the box could decide to tell us, say, I'm not going to move. So the box could choose to remain motionless. That's the first thing which could happen. The box can remain motionless. If it chooses to remain motionless, then the velocity of the box is going to be 0. As long as it continues to choose to remain motionless, then the velocity of the box will continue being 0. So if the velocity is always 0, then there is no acceleration along the x direction. So in that particular case, the acceleration along the x direction is 0 meters per second. The other case which would happen is that the box could move at constant velocity. So the pulling force might be large enough to move the box, okay, but only to move the box at constant velocity. So if the box moves at constant velocity, again, in this particular case, the velocity of the box will not change. It will remain whatever it is, okay, as it's moving at constant velocity. So in this case, again, the acceleration of the box will be equal to 0 meters per second. So in these two cases, when the box chooses to remain motionless, or when the box chooses or opts to move at constant velocity, these two cases have got an acceleration which is equal to 0 meters per second. The other case could be that the box could decide to change its velocity by moving faster or by slowing down. So if the box velocity changes, as in increases or reduces, that is what constitutes acceleration, because acceleration just refers to the change in velocity of an object which is in motion. So if the velocity changes, whether the change is an increase or the change is a decrease, it is still acceleration. Okay. So we've got three cases here. We've got a case when the box could remain motionless. We've got a case when the box could move at constant velocity. Then the case where the box could move faster or the box could slow down. In the first two cases, where the box remains motionless or moves at constant velocity, the acceleration along the x direction will be 0. If the box velocity increases or reduces, then there is acceleration there. And if whenever there is acceleration, we want to find out what is the acceleration. So let us start with the simple cases where we already know the acceleration. When the box remains motionless. When the box remains motionless, we know what the acceleration is. The acceleration is equal to 0, since there is no change in velocity of the box. So when you write Newton's second law of motion, for this case, where the box is motionless, we have the resultant force equals to the mass of the box multiplied by the acceleration. Now, whether the box is motionless, it's moving at constant velocity, or moving faster, the expression for resultant force, or the forces which make up the resultant force, remain the same. Our resultant force is the pulling force minus the friction force. So that bit will not change. Okay. So in this expression of Newton's second law of motion, we substitute for our resultant force, which is F minus F, the pulling force minus the friction force, then the mass of the box, whatever the mass is, we don't know, but we know that if it's an object, it's a constant mass multiplied by the acceleration. Since our thing is motionless, then our acceleration is going to be equal to 0 meters per second squared. So if you multiply this m, mass multiplied by the acceleration, you get a 0 this side. So you end up with F minus friction force. So this F is a pulling force, the FF is the friction force. When you take the negative friction force to the other side, you end up with this expression, wonderful expression. The pulling force is equals to the friction force. So this is what happens if you try to pull something, then that particular something you're trying to pull decides to remain motionless despite your efforts of pulling it. The reason why it is not moving is because your pulling force F is equal to the friction force. Now, this friction we are talking about is the friction an object has when it is motionless. And that friction is what is called static friction force. So in this case, when your box remains motionless, the pulling force is equal to the static friction force. We have an expression for friction, static friction force. The static friction force is equal to the coefficient of static friction multiplied by the normal force. We have just seen up here that the normal force Fn is always equal to the weight of the objects. So in this expression of normal force here, so we end up with normal force is equal to the weight of the object, which is equal to mg. So we can rewrite this expression mu s, which is static friction force, multiplied by mg, which is the weight. So in this case, we end up having an expression for the force with which you are pulling. If you are pulling, you're trying to pull something, you're pulling very hard, but this particular something is not moving. So in that case, this is what you have. Your pulling force is equal to the coefficient of static friction multiplied by the weight of that particular object. So that's the force with which you're pulling with. We are interested in the force because we already know what the acceleration is. So in this case, acceleration is 0. So the other case, any questions so far up to this point? Are we clear up to this point? Okay, so the other case you could come across is when the box, you're pulling the box, then the box decides to move. But it decides to move only with constant velocity. So if the box moves...
You can kindly repeat yourself for static force.
Static force? This friction? Static friction force. Static friction force is the force which opposes the movement of the box if the box is motionless. There is always friction whether something is moving or not. If the object refuses to move, then the friction which is opposing its movement is static friction force. And the static friction force is given by this expression, 20. The coefficient of static friction multiplied by the normal force. This is how always you get friction. Friction force is equal to the coefficient of friction multiplied by some normal force. So in this case, since we're talking about static friction, the friction an object has when it's motionless, then it is a coefficient of static friction multiplied by the normal force. We have seen that the normal force is equal to the weight of the box, and the weight of the box is equal to mg. Therefore, the pulling force will become equal to the coefficient of static friction multiplied by the mass of the object and g, which is just the weight. Is that clear? So if you try to pull something...
Yes, sir, thank you.
Yeah, if you try to pull... You're welcome. If you try to pull something, then that particular something still refuses to move. This is how much force you're applying. If the object decides to move, so when it's moving, it's changing its position. So if the position of the object changes because you are applying this pulling force, but the object is moving at constant velocity. If it's moving at constant velocity, again, in that particular case, the acceleration along the x direction is equal to 0 meters per second squared. We write an expression for Newton's second law of motion here. The sum of the forces along the x direction is equal to the mass multiplied by the acceleration along the x direction. The expression for resultant force along the x direction is still the same. We have a pulling force minus a friction force which is trying to oppose this pulling force, then equals to the mass of the object multiplied by the acceleration. Our object is moving at constant velocity. So if your object is moving at constant velocity, then the acceleration is 0 meters per second squared. So in this case also, what you end up is you end up with F is equals to minus FF equals to 0, like that. Then you take this minus FF to the other side, you end up with F is equals to minus FF. So again here, your pulling force is equals to friction force. But now this is a different kind of friction. because your object is now moving. The friction associated with an object in motion is what is called kinetic friction force. And that kinetic friction force, FF, is given by the coefficient of kinetic friction multiplied by the normal force. And we have seen that the normal force is equal to the weight, which is equal to the mass of the object. So our friction force and our pulling force in effect will become equals to the coefficient of kinetic friction multiplied by the mass of an object. Now, these expressions, pulling force equals to the coefficient of friction, kinetic, multiplied by the weight of the object, equation number 27, and equation number 22, they are very, very similar to each other. The only difference is that here you've got the coefficient of static friction, and here you've got the coefficient of kinetic friction. Now, it turns out that the coefficient of static friction is always greater than the coefficient of kinetic friction. Usually, the coefficient of kinetic friction has got values somewhere 0.2. So it's a very small 0.2, 0.5, 0.15. Those are the typical values of coefficient of kinetic friction. However, the coefficient of static friction has a much larger value, somewhere around 0.8, 0.75, 0.85, or 0.9. So, the fact that the coefficient of static friction is always greater than the coefficient of kinetic friction explains why, when you're trying to push an object which is stationary, it is much more difficult for you to push an object which is not moving than it is to push something which is moving. It's easier to push an object which is already moving because that particular object is experiencing kinetic friction, and kinetic friction depends on this guy, mu k, which is always less than the static friction force. The coefficient of static friction. Are we clear? So always, if people are trying to push something, you go and help them when something has already started moving, you're going to push less. But if you're trying to be help, yeah, you can push something when it's not moving. But pushing something which is not moving is much more difficult. So I'd advise you to push things when they've already started moving. You'll find it much easier. Are we clear?
Yes, sir, clear.
Okay. Now, the two cases we have looked at both have acceleration equals to 0. When the object is motionless, and also when the object is moving at constant velocity. However, you can also have your object move faster or move slower. So when your object moves faster or moves slower, in that case, you have a value of acceleration which is not equal to 0. How do you know that the acceleration is not equal to 0? The velocity has to change. So if the velocity increases or if the velocity reduces, then there is acceleration there. And if there is acceleration, what is causing acceleration is the fact that there is a resultant force. If the acceleration is equal to 0 meters per second squared, then there is no resultant force. The resultant force is absent. So in the first two cases, when the object is motionless or it's moving with constant velocity, the resultant force is not there. It's absent. In this case, we're about to look at, we have acceleration. If we have acceleration, then we are interested in finding out what the acceleration is. So in this case, that's what we want. So you have a expression for resultant force like this equals to the mass of the object multiplied by the acceleration of the object along the x direction. The expression for resultant force is the pulling force minus the friction force, which is equal to the mass of the object multiplied by the acceleration. So this is what Newton's second law of motion gives us. If you have this resultant force this side equals to the mass of the object times the acceleration. If there is acceleration, we want to know what the acceleration is. So we divide both sides by m. When you divide both sides by m, we end up having the acceleration to be equals to the resultant force, which is F minus FF, divided by the mass of the object. So this is how you use Newton's second law of motion. If a resultant force is present, you're going to use that resultant force to obtain an expression for that resultant force. Using that resultant force, you divide the resultant force by the mass of the object, then you get the acceleration. Are we clear? You divide the resultant force by the mass, then you get the acceleration of the objects. In this case, if, like in our previous cases we have looked at, if the pulling force is equal to the friction force, whether the object decides to stop or the object decides to move with constant velocity, in those two cases, if the pulling force is equal to the friction force, then F minus FF will give you a 0. This expression will give you a 0. 0 divided by M, you get a 0, so you get 0 acceleration. Are we clear? So for you to have acceleration, what you're seeing is that the pulling force has to be greater than the friction force. This F, the pulling force, has to be greater than the friction force, or the pulling force has to be less than the friction force. We are going to look at both these cases. The easiest case to look at is when the pulling force is greater than the friction force. If the pulling force is greater than the friction force, this F minus FF will give you a positive resultant force. So if you get a positive resultant force, then you divide by the mass. Then what you're going to get is a positive acceleration. This positive acceleration is what makes your object move faster and faster. So there's going to be an increase in the values of velocity of this object because the acceleration is positive. Similarly, if the pulling force is less than the friction force, then F minus FF, the friction force, is going to give you a negative resultant force because F is less than the friction force. So it's going to give you a negative resultant force. When the resultant force is negative, then you divide by the mass. What you're going to get is a negative value of acceleration. This negative value of acceleration will cause the velocity of your object to reduce. It will keep on reducing as long as the resultant force is negative until it becomes 0, until your object comes to a stop. Okay. Now, an interesting case when the pulling force is greater than, in reality, the easiest case you can have where the pulling force is less than the friction force is when there is no pulling force at all. When the pulling force is equals to 0. The pulling force being equals to 0 happens when an object is sliding. So you have got a flat horizontal surface, then you cause an object to slide on this surface. That object is not being pulled, but it's just sliding on its own. So there is no pulling force. In that case, your F is going to be less than your friction force. That is going to result in something like this. You're going to have an acceleration AX, which is equals to minus the friction force divided by the mass. Because of this negative, your acceleration is going to be negative. The other thing you'll notice as you go through your tutorials, because now I think people are looking at tutorials on Newton's second law of motion. As you go through your tutorials, you will typically find that the values of acceleration, the values of friction, the friction force is generally very small. It's small. It's not very large. It's not a very large force. So this very large force, this very small force, divided by the mass of the objects. So you're dividing a small force divided by the object is going to give you a small value of acceleration. This small value of acceleration is negative. So basically what you end up having is a small negative acceleration. With this small negative acceleration, what's going to happen is that if your object you'll be sliding, the velocity of this object will reduce slowly, but it will continue reducing until this particular object comes to a stop. So normally, what we are interested in, sometimes we'll ask you to find the stopping distance. If an object is sliding, it has got this much mass, it was moving with this velocity, then it comes to a stop, and this is a coefficient of friction. What is the stopping distance? Or we can go in reverse. We give you the stopping distance, then we tell you the velocity it had, then we ask you to find the friction force which is trying to stop this particular object. So either you can move forward or you can work out the problem in reverse. But the point really is this, that when an object is sliding, the acceleration of that particular object is equals to minus the friction force, whatever the friction force is. This particular object is moving, so this friction you're talking about here is kinetic friction force divided by the mass of that particular object. So you get your value of acceleration. With this value of acceleration, you can predict how far your object will go before it stops. You can predict what the velocity of the object is going to be at each and every point. Are we clear?
Yes, sir.
Yeah. So this is what we use Newton's second law of motion for. When you apply Newton's second law of motion, you're trying to make a connection between your resultant force and the mass so that you can get the acceleration. We are not interested in the mass because the mass of an object can always be weighed. Just get some object, you put it on a scale, then you find what the mass is. So no one is interested in the mass, and we are not interested in the mass. What we are interested in is the resultant force, because we can use resultant force when we divide it by the mass of the object to get the acceleration of that particular object. Using that acceleration, we can predict, using the formulas we have before, the v is equals to u plus at, the s is equals to ut plus half at squared, the v squared is equals to u squared plus 2as. You can use those formulas to predict how your particular object is going to move. Are we clear?
Yes, we are.
Okay. The next bit is an object which is supported by a rope. So like I mentioned earlier, this is another example of an object which you have. So this object has got mass m. Because it has got mass m, it has got weight, and the weight is pointing down. Right now, as things are, the rope is supporting the object. So the object is not moving. This rope is supporting the object because it generates a force inside itself. That's called the tensile force. So the tensile force lives inside this rope. Okay. There are no other forces evident in this particular object because it's not moving in the horizontal direction. So basically, if it's not moving in the horizontal direction, it means that there is no resultant force along the horizontal direction. The only forces present are in the vertical direction. So this is where we are going to find the resultant force. The other thing which comes in if you have a setup like this is you have to choose direction, because remember, you're trying to work out resultant force, and force is a vector, which means it has got direction. Which direction is going to be positive, which one is going to be negative? In this case, I am of the opinion that you choose the direction in which this object would go if the rope was not there. So if the rope was not there, let's assume that the rope gets cut, mysteriously gets cut, okay? This object will move down. So this object, the way it is right now, has a tendency to move down. It is being stopped from moving downwards by the tension in this rope. So we are going to choose the direction in which the object is moving, or would tend to move if it had its own way, which is downwards. We'll choose that to be positive. Then the opposite direction, that will be our negative direction. So in that case, our weight, Fw, becomes our positive direction, then our tensile force which is pointing up becomes our negative force. So with these two forces, we can work out a resultant force along the y direction. Okay, so here, so the resultant force along the y direction will be the result of the weight, which is positive, so plus Fw, plus then the negative tensile force like that. So our resultant force Fw becomes the weight of the object Fw minus the tensile force. So this is the expression of resultant force. With this resultant force, what we want, of course, the reason why you're looking for resultant force is so that you can use your resultant force in an expression of Newton's second law of motion, like here. Fy is equal to the mass multiplied by the acceleration along the y direction. So y, so like that. So this is the resultant force along the y, and we have an expression for that, which is Fw minus Ft multiplied by the mass of the object which is hanging from the rope multiplied by the acceleration. So that's what you get. So when you do that, you can get a bunch of things. There are a couple of things which can happen. Of course, again, in this case, our mass can remain motionless, just be happy hanging there, not going anywhere. Or our mass can move downwards. You can lower your mass downwards at constant velocity. So in this case, when the mass remains where it is, the acceleration of the mass is 0 meters per second squared. If you lower the mass downwards at constant velocity, again, the acceleration is still 0 meters per second squared. Or you can lower the mass downwards very fast. So in that case, when you lower your mass downwards very fast, there's going to be an increase in the velocity of the mass, and that will result in acceleration. So there are three cases. The first two, when the mass remains motionless, the acceleration is equal to 0. When you lower the mass at constant velocity, your acceleration is also equal to 0. So we start with the first case, when the mass is motionless. So when the mass is motionless, we substitute for our resultant force this side, which is the weight of the box minus the tensile force this side, equals to the mass multiplied by the acceleration. So in this case, our mass is motionless. Its position does not change, and the velocity stays the same. So the mass multiplied by the acceleration will give us a 0. So we end up having the weight of the box minus the tensile force equals to 0. So in this case, what you get is the tensile force equals to the weight of the box. So whenever you see an object with a certain mass hanging from a rope, and this particular object is just happy to be there, it's not changing its velocity, it's not changing its position, it's just happy to be there, that should tell you that the tension which has been generated in that particular object is equal to the weight of that particular object. Are we clear? That's what it tells from Newton's second law of motion. The tension in that particular object is equal to the weight of that particular object. This tension is generated by the rope. Are we clear? Next, you can decide to lower a mass at constant velocity. And the lowering and lifting of masses at constant velocity is exactly what elevators do. If you have been in an elevator before, an elevator takes you up or down at constant velocity. This elevator is a box you get in, and that box has got weight. There is the actual weight of the elevator. There is also the weight of the people inside that elevator. Then there are cables pulling the elevator up and down. So if you move your mass, which is, let's say, the elevator in this case, up or down at constant velocity, then the acceleration is also going to be 0 meters per second squared. Please. So in that case, if the acceleration is 0 meters per second squared, you substitute for the resultant, which is the weight of the box, minus the tension equals to the mass multiplied by the acceleration. And again, in this case, you end up having the weight minus the tensile force equals to 0. So with this expression, you end up having the tensile force being equals to the weight of the box. So again, in the case where your box moves up or down at constant velocity, if your box moves up or down at constant velocity, so in that particular case, the tension is also equal to the weight of the box. So whether the box stays motionless, supported by a rope, or the box moves at constant velocity, the tension is the same. It is equal to the weight of the box. Are we clear?
Yes, sir.
The tension is the same in the rope. Then lastly but not least, you can decide. I think I've seen movies where a cable in an elevator cuts, one or two cables cut, then the elevator decides to move faster. So you can have a case like that where something moves faster. Either it's falling faster, but it's supported by cables or ropes, or it's being risen, it's rising faster. Okay? So in that case, there is acceleration. The velocity of the object is increasing. If the velocity of the object is increasing, then you want to find out by how much is the velocity increasing. So in that case, since the velocity will increase, there is acceleration, and you want to find what the acceleration is. So we substitute for the resultant force, which is the weight of the box minus the tensile force, equals to the mass multiplied by the acceleration. In this case, this you can find. Okay? What we are interested in is how do you get the acceleration. So the acceleration in this case, since you have an expression of tensile, so you have an expression of resultant force this side, Fw minus Ft, what you want is the acceleration. So you divide both sides by m, so that you get Ay is equal to the weight minus the tensile force in the rope divided by the mass. So this is going to give you an expression of your acceleration. When there is acceleration, for acceleration to happen, okay, the weight of the mass and the tensile force cannot be the same. For acceleration to happen, this guy, Fw and Ft, cannot be the same. The weight has to be greater than the tensile force. So these two guys have to be different. The weight has to be greater, especially if something is being lowered, it's going down, and it's moving fast. The weight has to be greater than the tensile force. Otherwise, if those things are equal, then you will not have acceleration. So what you end up having is you'll be moving at constant velocity. Are we clear?
Yes, sir, we're clear.
Is there any question? We have come to the end of this bit, Newton's laws of motion. Is there any question? If there are no questions, then we'll stop here. We'll upload the recording to YouTube. Then you see it from there.
Sir,
Yes.
sir, the question.
Yes.
What's the recommended book for physics?
What is the recommended book for physics?
Yes.
Well, in my opinion, where I am, the best physics book is Principles of Physics by Buch. The only problem is, at your stage, I don't think you can understand it, what it is they're trying to say. That's the only thing I have. But after you finish first year physics, if you're going to read a physics book, the best one is Principles of Physics. But usually most students at your stage, they don't understand things. But I think with these explanations we have given you about certain things, you should be able to understand things better. There are a lot of books. There is a book which Mr. Chimba is selling with Professor Manyara in the physics department for 150. You can try to give that a look, because they also try to tackle some things, explain things better. So I think you can try to see that. But yeah, that's all I have to say. You have to understand things so that you can solve your problems. Okay. Any other question apart from the recommended books? The best book is Principles of Physics, in my opinion. Yeah. Okay, so if there are no other questions, then we'll end here. The recording will be available on YouTube shortly. Is there a question?
Yeah, there's a question, sir.
Yes, go ahead.
Can you use the equation of kinetic friction to equate it to the equation of static friction?
No, you can't. They can't be the same.
All right.
Yeah, they are never the same. One is greater than the other. Static friction is always greater than kinetic friction. Any other question? Okay, so if there are no questions, we'll stop here. See you tomorrow, same time. Okay. All right, cheers. See you tomorrow. So stop sharing.